When modern cities lose power, water can stop flowing within hours. Yet thousands of years ago, entire civilizations delivered clean water without electricity, pumps, or plastic pipes. Ancient Rome supplied millions of liters daily using nothing but gravity, while Persian canals carried groundwater across deserts for centuries with almost no maintenance. Some of these systems still function today, while many modern pipelines fail after a few decades if repairs are delayed. This creates a disturbing question. Did ancient engineers understand water systems in a deeper, more durable way than modern societies that rely on advanced technology? Early civilizations formed where water could be controlled, not merely accessed. In Mesopotamia, irrigation canals were carefully graded to manage river flow and prevent flooding. These were not rough trenches, but planned systems requiring mathematical understanding and collective coordination. Mistakes meant crop failure and famine, so accuracy was essential. Water management became a foundation of law and governance, showing that engineering knowledge was central to survival, not an afterthought. In ancient Persia, engineers developed qanats, underground tunnels that transported groundwater from mountains to dry plains over distances that sometimes exceeded 40 kilometers. These tunnels relied on precise gradients. If the slope was too steep, collapse occurred, and if too shallow, water stagnated. By keeping water underground, evaporation and contamination were minimized. Many qanats remain operational today, proving that their builders understood geology and sustainability with remarkable precision. Roman aqueducts expanded this logic on a massive scale. Most aqueducts ran underground and followed extremely gentle slopes, allowing gravity to move water smoothly over long distances. Rome eventually relied on multiple aqueducts that fed public fountains, baths, and sanitation systems. Continuous water flow reduced stagnation and improved cleanliness. Roman engineers carefully selected spring sources far from pollution and protected them through strict regulations. Elsewhere, the Indus Valley civilization demonstrated a different kind of intelligence. Cities such as Mohenjo-daro featured household wells, bathrooms, and covered drainage channels connected to larger municipal systems. Wastewater flowed away from living areas through gravity-fed drains built with standardized bricks and access points for cleaning. This level of urban sanitation would not reappear in many parts of the world for thousands of years. Across these civilizations, a shared pattern emerges. Ancient water systems were designed to last, to work with natural forces rather than overpower them, and to remain functional even when political or social conditions changed. They were visible, maintained by communities, and deeply connected to daily life. Understanding this foundation is essential before comparing ancient intelligence to modern plumbing, because only by examining how ancient systems actually functioned can we fairly evaluate what progress truly means. Ancient and modern water systems begin to diverge most clearly when purity, pressure, and waste management are examined side by side. A common assumption is that ancient water was unsafe, while modern water is inherently clean, but historical evidence complicates this view. Ancient societies focused heavily on protecting water sources rather than treating contaminated water later. Roman engineers sourced water from distant springs instead of rivers passing through cities, reducing exposure to waste. Persian canals filtered water naturally as it moved slowly through layers of soil and rock, removing sediments and many impurities before the water ever reached settlements. This approach relied on prevention rather than correction, a principle still considered essential in modern environmental engineering. Modern plumbing systems take a different path. Water is often collected from sources already exposed to agriculture, industry, and urban runoff, then treated chemically before distribution. While filtration and chlorination are effective, they introduce dependence on constant monitoring and perfect operation. If treatment systems fail or pipes deteriorate, contamination can return after water has already been declared safe. Incidents involving lead, bacteria, or chemical exposure in modern cities demonstrate that advanced treatment cannot fully compensate for aging infrastructure. Ancient systems lacked laboratories, yet their emphasis on clean sources often reduced risk at the beginning of the process rather than at the end. Pressure highlights another philosophical difference. Ancient engineers avoided high pressure whenever possible because they understood its destructive potential. Roman aqueducts maintained slow, steady flow using gentle gradients, minimizing stress on channels. When pressure was unavoidable, such as in valley crossings, inverted siphons were carefully calculated and used sparingly. Modern plumbing depends on constant high pressure supplied by electric pumps. This guarantees convenience but accelerates wear, increases leakage, and requires continuous energy input. Large volumes of treated water are lost daily through underground leaks that remain invisible until severe damage occurs. Waste removal further separates ancient resilience from modern efficiency. Roman cities used gravity-fed sewers that flushed waste continuously using surplus water from aqueducts. The Cloaca Maxima, built over 2,000 years ago, still exists today. While ancient waste often entered rivers, so did modern waste until relatively recent history. The difference lies in scale and concentration. Ancient populations were smaller and systems more distributed, limiting widespread failure. Modern sanitation relies on centralized treatment plants that serve millions. When such facilities fail, the consequences affect entire regions at once. Maintenance culture also played a critical role. Ancient systems assumed regular human involvement. Roman aqueducts employed full-time inspectors and repair workers, while canals were maintained by local communities who depended directly on their function. Modern systems are designed to operate invisibly. Pipes are buried, infrastructure is hidden, and maintenance is often postponed for political or financial reasons. Failures appear sudden, even though deterioration developed slowly over decades. These differences reveal that ancient intelligence focused on stability, visibility, and long-term survival, while modern systems prioritize speed, scale, and convenience. Neither approach is inherently superior, but they reflect different responses to risk. Ancient societies faced immediate consequences for failure, while modern societies often defer consequences into the future. This contrast sets the stage for the final comparison, where modern plumbing is tested under stress and ancient principles quietly re-emerge as possible solutions rather than relics of the past. As modern plumbing expanded, especially across North America, it came to symbolize progress itself. Indoor water, instant pressure, and centralized treatment created an expectation of reliability that shaped modern life. Yet the true measure of intelligence is revealed when systems face stress. Power outages, extreme weather, aging infrastructure, and climate instability expose how dependent modern water systems are on constant energy and institutional support. When electricity fails, pumps stop. When funding is delayed, pipes corrode. Entire cities can lose safe water within hours, not because knowledge is lacking, but because the system was never designed to function without continuous intervention. Much of today's infrastructure was built decades ago with the assumption that future replacement would happen on schedule. In reality, replacement is often postponed, allowing hidden decay to spread inside pipes and joints. Corrosion releases metals, pressure worsens fractures, and treatment plants are forced to compensate for delivery failures they were never meant to handle. Ancient builders assumed the opposite. Their systems were designed to outlast political change and human lifespans. Gravity-fed flow did not depend on fuel, and materials like stone and concrete degraded slowly and predictably rather than suddenly. Climate pressure further reveals the contrast. Many modern systems were designed for stable rainfall patterns and moderate temperatures. Drought lowers reservoirs, floods overwhelm treatment plants, and extreme cold or heat damages pipes. Ancient systems were often built with seasonal variation in mind. Cisterns stored excess rain, underground channels protected water from heat, and stepwells accounted for long dry periods. These designs did not eliminate variability, they adapted to it. Modern systems often resist variability until resistance becomes impossible. Population scale complicates the comparison but does not erase the lesson. Modern cities serve millions, requiring efficiency and coordination unknown to ancient societies. Yet scale does not require total centralization. Ancient systems favored distribution and redundancy. Failure was local rather than catastrophic. Increasingly, modern engineers are returning to this logic through decentralized treatment, rainwater harvesting, and gravity-assisted flow. These ideas are often framed as new solutions, but they closely resemble ancient practices refined by necessity. Public awareness also matters. Ancient people saw their water systems daily. Aqueducts, wells, fountains, and drains were visible parts of urban life. This visibility created respect and accountability. Modern plumbing is hidden underground, distant from daily awareness. When failures occur, they feel sudden and inexplicable, even though warning signs existed for years. Distance from infrastructure creates distance from responsibility. So who was smarter? If intelligence is measured by speed, scale, and convenience, modern plumbing clearly excels. If intelligence is measured by durability, energy independence, and alignment with natural limits, ancient systems demonstrate extraordinary insight. The difference lies in priorities. Ancient societies optimized for survival under constraint. Modern societies optimize for abundance under assumption. The most honest conclusion is that progress is not a straight line. Modern water systems achieve remarkable things, but they increasingly depend on ancient principles to remain sustainable. Gravity, simplicity, redundancy, and respect for natural limits are no longer relics of the past. They are guides for the future. Ancient water engineers were not wiser because they were primitive, but because necessity forced clarity. Their systems remind us that true intelligence is not how advanced a system appears when everything works, but how quietly and reliably it continues when conditions no longer cooperate.